I'm here to present a seminar topic on course PCT A12. Topics explain the characteristics of Bingham plastic flow and its examples. Abstract learn about Bingham plastic flow, a fluid behavior where material like toothpaste and mud flowed only after exceeding a heat stress threshold. Like understanding Bingham plastic flow. This pretend to be a type of fluid behavior characterized to certain material that do not start flowing until a certain stress threshold known as heat stress is excited. This model is pivoted in describing the flow behavior of material like toothpaste, mud, draining fluid and certain suspension. This basically like this basically do with fluid like toothpaste and other toothpaste and ketchup. Like this fluid they are not easily they cannot easily wash away unless like you applied a exact force on it. And this study the study deals with an investigation of the fluid of a Bingham plastic fluid in a porous bed until under the action of an external magnetic field. Porosity of the bed has been described by considering Bingham method model. Both steady and pulsatile motion of this non-Newtonian fluid have been analyzed. This governing equation are solved numerically by developing a suitable finite difference scheme. As an application of the theory of the field of magnetic thermology, he said physical variables have been computed by considering the value of the involved parameter for blood flow in the pathological state. When the system is under the action of an external magnetic field, the pathological state corresponds to a situation where the liman of an arterial segment has turned into a porous structure due to formation of blood clots. Numerical estimates are obtained from the velocity profile and volumetric flow rate of blood, as well as the shear rate. In this case of blood flow, it is described author, author, but the velocity and volumetric flow rate diminish in the strength of the external magnetic fluid is enhanced. This the study further shows the blood velocity is maximum in the plug core region. It described monotonical as a particle of blood travels toward the wall. The study also bears the potential of providing numerical estimates for many individual fluids that follow big arm plastic model, which the value of different parameters are chosen appropriately. And we have velocity and heat stress. This velocity is the measure of the fluid resistance of gradual deformation of shear and tensile stress. For Bingham plastic, this concept is extended with the addition of heat stress, which is the minimum force needed to start the flow. Below the stress, a Bingham plastic behave like a solid Above it, the material flowed like a viscous fluid. The mathematical expression typically used to describe the behavior is sorry, where T is shear stress applied, T square is the yield stress, where we have the plastic and velocity, and we have the shear stress also. In material science, the Bingham plastic is a viscoplastic material that behaves as a rigid body at low stress but flow in a viscous fluid at high stress. It is named after Engine C. Bingham, who proposed its mathematical form in 1916. It is used in common mathematical model of mode flow in drilling engineering and in the aiding of soiling. A common example is toothpaste, which will not be extruded until a certain pressure is applied to the tube. It is then pushed out of the elective unerrant plug. And we have the figure, the table that shows the Bingham plastic flow as described by Bingham, like the man that described it in 1916, as it show a graph of behavior of an original viscous fluid in red. For example, in a pipe of a pressure at one end of a pipe is increased. This process a stress is the fluid tending to make it move, cause the stress excess stress, and the volumetric flow rate increasing properly. However, for a Bingham plastic fluid in blue, that is, stress can be applied but it not flow until a certain value, like this the E stress is reached. Beyond the point of flow rate increasing steadily with increasing stress rate. This is roughly the way in which Bingham presents the observation. In an experimental study of paint, this property allow a Bingham plastic to have a textured surface which peaks and ridged instead of a featureless surface like a Newtonian fluid. And we also have the figure 2 which show the tables which describing the shear stress and the shear rate and the yield stress too also. It shows the way in which the normal presenting currently. The graph show shear stress on the vertical axis and shear rate on the horizontal one. Volumetric rate depends on the size of the pump. Shear rate is the measure of how the volumetric change the distance is properly of low rate but not but does not depend on the pipe size as as before. The Newtonian fluid flow has give a shear rate for any finite value of shear stress. However, the Bingham plastic again does not exhibit any shear rate, no flow or no velocity until a certain stress is attached. For the Newtonian fluid, the slope of the line of the velocity, which is only parameter needed to describe its flow. By contrast, the Bingham plastic requires two parameters: the yield stress and the slope of the line, known as the plastic velocity. The physical reason of the behavior is the liquid certain particles such as clay or large molecules such as polymer which have some kind of interaction creating a weak solid structure formerly known as the force body, and a certain amount of stress is required to break the structure. Once the structure has been broken, the particle moves to the liquid under viscous force. Is stress is If the stress is removed, the particle associates again. The material is an elastic solid of shear stress less than a certain value. One of the critical shear stress or yield stress is exerted. The material flow is such a way that the shear stress, that is the UDY, is defined as the article on velocity and viscosity. The the directly proportional of the amount by which the applied shear stress exceeds the yield stress. And we also have a frictional factor formulae in fluid flow. A common problem of the calculation is pressure drop in an exhibiting piping network. Once the frictional factor is known, it becomes easier to handle. Different pipe flow problem involves calculating the pressure drop and evaluating pumping cost, or to find the flow rate in the piping network for a given pressure drop. It is usually extremely difficult to arrive at exact analytically solution to calculate the friction factor associated with flow or non-Newtonian flow, and therefore explicit approximately are used to calculate it. One of the friction factor has been calculated with pressure drop can be easily determined for a given flow. We have the formula of the frictional factor, which is yeah, the mean, and we have the why is the frictional head loose SI unit M, and is the gravitational acceleration SI unit M S raised to power 2, is the pipe diameter SI unit M as meter, is the pipe length SI unit M as meter, in the means fluid velocity, that is ms, that is meter per second. Combine equation for frictional factor. We have sorry, in 1981 Darby and Malson, using the approach of Corsill and of Churchill and Hugi, developed an expression to get a single frictional factor equation valued for all flow regions. So the equation has m is equal to 1.7 of, and we have the references and conclusion. Thank you.
Clap your hands if you want to clap. What are you doing? All right, thank you very much for the presentation, but you still have a lot of work to do in your presentation style. Am I communicating? So when you're coming out for next topic, prepare your work well. So you'll be able to communicate. The communication is not that wonderful, and the listening to what you are saying, it made sense, but you didn't present it well. So work on your presentation style so that you can carry the audience along. Is that clear? So please don't forget that this is an academic exercise. So through this, you learn on how to communicate in public, how to present anywhere you see yourself tomorrow. So work on that. It's very important. Okay. All right. Please, can we clap for him again? Thank you very much.